Okay, I thought just for fun, from question, I think it was question 6, the last question on the first problem sheet, we used a little bit of calculus, and some people said that they were pretty fine with it, or it was all coming back over time. Other people said that they weren't really 100% across it. So first, to reassure you, you really can get away quite adequately without having the calculus layer for senior physics. You can basically use algebra and trig to do pretty much everything we need to do. But it is quite helpful to have that, at least the quite initial calculus layer, just because it actually explains things so nicely around motion in particular, but around a number of things, so accelerations and so on. So I thought what I would do is just give you a little bit of a refresher for those who've done it before, and probably not enough for someone who's never encountered it before, but just a little sense of the tool and what it's for. So in this case, let's take an example. It's a little bit simpler and neater looking than the example that was in question 6 of the first of problem sheet 1.2. So we're asked the velocity of an object is given by v at t. The velocity at time t is t squared minus 1. So first graph the object's motion. Okay, so we're graphing t on the x-axis and v at t, or just v, on the y-axis. So it's a velocity versus time graph. We could have done a displacement versus time graph or an acceleration versus time graph. This particular one happens to be velocity versus time. So to graph it, what we'll do is pick some typical points. So we know that vt, when t equals 0, that t squared term goes to 0. So at t equals 0, which is 0 along the x-axis, the point is minus 1 on the vt axis. So we know that that's a point on the line. When t equals 1, t squared equals 1, 1 minus 1 is 0. So we know that our line goes through this point, 1, 0. I should label these points. So this is, naming the x-axis first, the point minus 1, the point 0, minus 1. And this one is the point 1, 0. And if we put in t equals 2, we could do this as a little table if we wanted to, just some test values of t. So for t equals 2, 2 squared is 4, minus 1 is 3. So at t equals 2, it's going to go through the point 2, 3. And what did we say? From t equals 0 to t equals 3. So for t equals 3, 3 squared is 9, minus 1 is 8. So it's also going to go through the point 3, 8. Now we really test my drawing on the tablet skills to try and make a smooth curve through these. It's not a smooth straight line because it's an x squared curve. So I'm going to try and smoothly curve. Oh wow, that's shonky. Up through that. That shape should be a parabola because it's an x squared term, and it would actually go that direction. Okay, and we're back after the phone rang and I answered it, and I've tweaked my graph a little bit to make it a little bit prettier while I was not recording, but it's still not 100%, but you know, what are you going to do? So that's our graph. So that's the way in which the velocity of the skater changes over time. So that actually means that down here, the velocity is negative. In other words, it's in the direction opposite to the direction that we're choosing as positive. Remember that our directions are relative. We can choose whichever direction we like as positive. And then from here on, the slope is positive, but the number is still negative. So our velocity at t equals 0 is negative 1. So it's still going in that negative direction. It's not until we get up to here that it goes to 0 velocity. Remember that this is a velocity axis and this is a time axis. So the velocity is negative here and positive here. Sorry, still negative here, positive here, and on up is the velocity. And the velocity then steadily increases. That slope should be, if my graph was good, steadily increasing as a power of t squared. So what are we asked? Graph the object's motion for the time from t equals 0 to t equals 3 seconds. So we've done that with a little bit of a bonus tail over here. So but from t equals 0 to t equals 3 seconds. Calculate the object's acceleration at t equals 2 seconds. So t equals 2 seconds is this point here. I'll get my handy dandy ruler and try to draw a tangent to the line at that point. Now this is very tricky because the ruler is not on a screen where I can see what's going on. It's on a tablet which is separate to the screen. So a little bit complicated, but a little bit slopier. Okay, so I'm drawing my tangent line should be all outside the curve. Maybe I'll draw it freehand instead of with the ruler because that's maybe easier. So I do apologize for the shortcomings of the technology here. So a tangent should be outside the line and it should have the same slope as the line at that point, and it should be a straight line. So that notionally at least is a straight line touching the curve at the point t equals 2 seconds, and that straight line is going to be the gradient of the line, and that's going to be the acceleration of the object at that moment. The slope of a velocity time graph is equal to the acceleration. So and why is that? What are the units? So our units for velocity are meters per second. Our units for time are seconds. To find the gradient of a line, you go, rise, the vertical distance it rises, divided by run. So the rise is the velocity in meters per second. Oops, 1 there. The run, the distance it travels horizontally, is the time in seconds. Now, the A equals velocity, or change in velocity over change in time, is something we're already familiar with. That's the definition of acceleration. Time in seconds. Now, if you divide meters per second by seconds, you get the unit meters per second squared, meters per second, which is the unit of acceleration. Right, so we're happy with that the slope of a velocity time graph is going to be an acceleration. So that's part B of this question, is calculate the object's acceleration at 2 seconds. Now, this is where the calculus comes in. Calculus is a tool for calculating, at least initially. So differentiation is a tool for calculating the gradients of lines, the slope of a tangent at a particular point. And we know that, let's see, in this case, v equals t squared minus 1. Now, we can write, there's a couple of different notations, so that may be something that people find a little confusing. We could write it as dv by dt, the rate at which v changes with respect to t, so dv dt. You will have been familiar with lots of equations where it's dy dx, if the equation is in terms of y and x, but in this case it's in terms of v and t, so it's the same thing. So dy dx or dv dt is going to be, and I'll calculate that derivative in a minute, or the other one we use is a little prime, so v prime, and it means the same thing. It means the derivative of. Now, we know that for derivation, if we've got, let's see, if we've got t to the power n, if v equals t to the n, then dv dt equals n t to the n minus 1. So in other words, we take that power, we bring it down to the front and multiply, and then we subtract 1 from it. And that's true for all of our terms. So in this case, we've got t squared, so n equals 2. So we bring that down the front, 2t, and then we go 2 minus 1 is 1, t to the power 1. We don't usually bother writing exponentials of 1 because t to the power 1 is just t, right? So we do that. This is also a power of t. It's t to the 0. Of course, because it's t to the power 0, you multiply by 0, so that term just disappears. So constant terms just disappear when we differentiate. So in this case, t squared minus 1 just goes to 2t when we differentiate it, and that's the same no matter what the notation we're using, either this or this. So, all right, so that's told us that that is going to give us the slope at any point for any value of t. So if we had at t equals 0, if you go up here, at t equals 0, the slope is 0, right? So that works. At t equals 1 second, which is here, that slope should be equal to 2. So if I was to draw a tangent to the line at that point, it should have the slope 2. It doesn't quite because my graph is not perfect, but that would be what it would actually be. But we're interested in t equals 2 seconds. So the acceleration is just this derivative, we'll call it v dash, is equal to 2t. And we're evaluating it at the time t equals 2 seconds. So it's 2 times 2 equals 4 meters per second squared. Right, so that's part B. Part A was graphing the expression. Part B was conducting this derivative and finding the acceleration, and the acceleration is 4 meters per second squared. So we're happy with that, I hope. Now, differentiating simple polynomials like this is relatively easy with the nx to the n minus 1 or nt to the n minus 1 rule. But also we can differentiate trig expressions, so derivative of sine is cos and cos is minus sine, or is it the other way around? I always have to look that one up. Derivative of e to the x is e to the x, which is kind of cool and unusual, and so there's a whole variety of bits and pieces that we could do, but just remembering that we've got this tool that if we have a velocity time, we can actually calculate the acceleration using calculus is quite cool. And then we're also asked to find how far, this is part C, calculate the distance the object moves between t equals 1 and t equals 2 seconds. Well, I'm going to try to clean things up a little bit, get rid of some of this material because it's a little untidy. Okay, and I'll get rid of that as well. All right, so to find out between t equals 1 and t equals 2 seconds, we've got, there's t equals 2, there's t equals 1, and it turns out that the area under the curve is the displacement. So now we'll work that out the same way again. So in this case, s, the displacement, which is measured in meters, is equal to, in this case we're doing an area, so it's, we multiply the two things rather than divide them. So the distance across is going to be t in seconds, and the height of that thing is going to be, so we're multiplying by v in meters per second. So in this case, the seconds and the seconds to the minus 1 cancel out, and we end up with a distance in meters as the units. So that's correct too. So what we want to do is find the area under this curve. Now I could go into the whole how we get integration by taking slices and then making them smaller and then taking limits and all that kind of stuff. But for our purposes, all we need is the method that we use to do the thing, which is really just the opposite of what we just did with the differentiation. So let's scroll down to where we have some room and figure out the area under that curve, which will be that displacement. So this is part C. Again, we've got v at time t equals t squared minus 1. Now, the displacement, s, is going to be an integral, and we're asked for the period between 1 and 2. So this is a definite integral. If we didn't know the period that we were interested in, we could do an indefinite integral, and we would have to add a constant. It gets slightly more complicated, but not very much. But in this case, we have a definite integral. We want to know the time between 1 and 2, so we know where our start and finish points are. And for integration, so the integral of t to the power n with respect to t, so we just put in the dt, is 1 over n plus 1 t to the n plus 1. So we're effectively doing the opposite to what we did with differentiation. So in this case, I'm going to go, so we've got the integral there of t squared minus 1. That's the overall expression. With respect to t, that's just telling us what we're differentiating with. We're not differentiating with respect to s or v or anything else. Sorry, integrating with respect to. So in this case, with the 1 over n plus 1 t to the n plus 1, we're going to evaluate it between 1 and 2, as we already said. That first term, 2 plus 1 is 3, so it's 1 over 3 t to the power 3. And then this, remember I said, is 1 times t to the 0. If we add 0 to, or 1 to 0, we get 1. So it's 1 over 1 times t to the power 1. Now, we tend not to write either of those things. 1 over 1 is just 1. So, and 1 times anything is itself, so we don't bother writing it in. And to the power 1 is also just itself, so we don't bother writing it in. So I'll get rid of that. So that's our actual expression, is 1/3 t cubed minus t. So we need to then evaluate it at 2 and evaluate it at 1 and subtract. So that's going to be 1/3 of 2 cubed minus 2 minus 1/3 of 1 cubed minus 1. So that is 8 over 3 minus 2, and 2 is 6 over 3. Just making the fractions a little bit easier. Minus 1 over 3 minus 3 over 3 equals, so that's going to be plus 2/3. That's going to be minus 2/3. That's worrying me. That looks like it's going to be 0, but no, it's actually not, because 2/3 minus 2/3, it actually adds up to 4/3 of a meter. In other words, 1 1/3 meter, 1.33 meters, 1.33 repeating meters is our actual displacement. If we go back up, that's the area under the curve in that little piece between t equals 1 and t equals 2. And we've actually used our differentiation to calculate the acceleration at a point, and we've used our integration to calculate the displacement between two particular points. Hope that's helpful. Hope it's been kind of a long video with some kind of messy calculations, but hopefully that gives you a little bit of a sense of this particular set of tools and what they're helpful for.